So in an electrically neutral atom, so an overall charge of 0, the number of protons equals the number of electrons. But this may differ from the number of neutrons. So that's the important part. It must be electrically neutral for the protons to be equal to the number of neutrons. Now if we start from this premise, we can actually make some definitions. Firstly, that the atomic number, which is denoted with a capital Z, is unique to an element. In other words, there is only one Z per element. And it's equal to the number of protons. Now this is often confusing for people because they assume it's the number of electrons within that atom that gives it the atoms of an element are unique based on the number of electrons. This is incorrect. It's based on the number of protons. And we denote this atomic number Z. We've also got another quantity as well, and we call this one the mass number and denote it with a capital A. And A, or the mass number, is equal to the number of protons plus the number of neutrons. So we're talking about what's in the centre of the atom, or the nucleus. And we do this because this is 99.95% of the mass of the atom. This number may actually vary within one element. So we said before that each element has a unique atomic number. There may actually be a few mass numbers for each atom. So we have different types of atoms that vary not in their atomic number, the number of protons, but in the number of neutrons. And this forms what is known as isotopes. Now, if we were to put this diagrammatically, we can actually represent an atom with our atomic number and our mass number. And this is often what we see on the periodic table. We'll have an element, in this case we've got carbon. We'll have our atomic number represented at the bottom. In this case it's 6, it has 6 protons. And we have a mass number, which is the number of protons plus the number of neutrons, and that's represented as our A. So let's have a look at our first 10 elements. We've got hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So in order from simplest, so atomic number of 1, to most complex in this situation, where our atomic number is 10 for our neon. So our first column is the number of protons, or our Z number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, denoting the increase in protons. We've then got the number of neutrons associated. So we find our hydrogen has 0, but this can actually vary, and we can get isotopes, as we mentioned before, that may have 1 neutron or even 2 neutrons. This is the most common form. Helium, 2 neutrons, lithium 4, beryllium 5, down to neon, which has 10, the same number as fluorine, in its most common form. If we shift across to our next column, the number of electrons, and this is an electrically neutral atom. So for our hydrogen, we will have the same number of protons and electrons. Our helium will have the same number again, and we notice that we've got it all the way down to neon. Now I've put an asterisk here because we can actually change the number of electrons. So we've got to move away from that idea that an element or the atomic number is based on electrons. It's actually based on our protons. And the final column is our mass number, which, as we said before, is the addition of our number of protons and neutrons. So 1 plus 0 is 1, 2 and 2 is 4. We keep moving down to oxygen, 8 and 8 gives us 16, neon 10 and 10 gives us 20. So we can use this information to determine atomic number and mass number. So I've got a little question like this. A sodium atom consists of 11 protons, 11 electrons and 12 neutrons. We want to know the atomic number and the mass number for sodium in this case. Well, our atomic number, as we said before, is equal to the number of protons. So in this case we have 11. And our mass number is equal to the number of protons plus the number of neutrons. So we have 11 plus 12 gives us the 23. So to represent this particular element, we might draw like we have on our periodic table. It's sodium, Na, and we would have 11 And that's how we use the information given in a table like this to determine our atomic number and mass number.